So far we have talked about various forms of averages, but of course we might also be interested in the spread of the points around, for example, the expected value. And the quantity that would explain us that or give us that is the so-called variance. The variance var of a random variable x is defined by, again, an expected value of the square of the difference between x, the random variable itself, and its expectation. So we're taking an average squared deviation. So this is the deviation, the difference between x and e of x is the deviation between the values of x and the mean of x. We're squaring that and taking the average of it. So the expected value over the variable x. Now, using linearity of the expectation, it is straightforward to show that the variance of x, this expected value here, the expected squared deviation, is equal to the expected value of x squared minus the expected value of x and then squared. We can briefly derive that. So e of x minus e of x squared is equal to e of x squared minus 2x ex plus e of x squared. We have a sum of 3 terms. We can take the expectation of each of them. So this is equal to e of x squared minus 2 e of x e x plus e of x squared. And of course we would also take the expectation of this, but the expected value already is not a random variable anymore, it's a constant, so the expected value goes away. Now let's take the expectation of this term here. The expected value of the product between x and e of x. E of x is, as we said, just a constant, so we can pull it out of the expectation, which means that we get 2 times the expectation of x times the expectation of x. So this is equal to e of x squared minus 2 times, well, e, the expectation of x times the expectation of x is equal to the expectation of x squared plus the expectation of x squared, well, plus 1 minus 2 is equal to minus 1 is equal to e of x squared minus e of x squared. Exactly what we wanted to show. Now variance is useful because it gives us an idea of the spread of a distribution. However, the problem with variance is that it scales as the square of the units of the variable. So it's not easily comparable with the mean and not easily comparable with the values that x takes. Now the quantity that does give us this information is the so-called standard deviation. And the standard deviation is defined as the square root of the variance. The standard deviation now has the same units as x itself. The variance is a property of the random variable. If we have an empirical sample, say n examples of the random variable x that are drawn identically and independently from the distribution of x, then we can use these to get an estimate of the variance. And the so-called empirical variance is this estimate given by 1 divided by n, so it's the average over our n data points, times the sum from n equals 1 to n, the difference between xn and x bar squared, where x bar is defined as the average of x. So it's 1 divided by n, sum n equals 1 through n xn. Now, note that x bar was the empirical mean. Which itself is an estimate for the unknown expected value of x. So we are using an estimate of the expected value in an estimate of the variance. Because of the fact that this is the case, there is a small downward bias in the variance estimate. So in the empirical variance tends to be slightly smaller than the real value on average. And for that reason, there's also a separate second common estimate of the variance, which is the unbiased variance estimate, which is given by almost the same formula, just that instead of dividing by n, we're dividing by n minus 1. So just note that this is the so-called unbiased variance estimator. And this is the so-called empirical variance. Now, if the data set is large enough, so if n is sufficiently large, then they will be almost identical, then it doesn't matter. But for small n, so for small sample sizes, these might be different from each other, but they're both commonly used. The variance tells us something about the spread of a variable around its mean. If we have multiple variables, then their so-called covariance tells us about how they move together. So the covariance is a measure of the linear relationship between two random variables. It's typically denoted by cov, so for two random variables x and y, cov x, y is defined as the expectation of the product of x minus ex and y minus ey. So it's the expected value of x minus its mean times y minus its mean. Note that so far we've only looked at single variables. In this case, we're looking at two variables. So the outer expectation must be taken about the joint distribution of x and y. Similarly to the formula for the variance, the covariance can also be rewritten as the expected value of the product x times y minus the expectation of x times the expectation of y. By expanding the term here and applying the linearity of the expectation. If we compare the formula of the covariance to the formula of the variance, we see that the variance of x is equal to the covariance of x with itself. So remember that the covariance of x was the expected value of x squared minus e of x squared, which is exactly the covariance of x and x. A useful property of the covariance is bilinearity. What does this mean? Well, if we take the covariance of the weighted sum of two random variables x and y with a third random variable z, so covariance of alpha, the weight applied to x, plus beta, another weight applied to the random variable y, and we're measuring the covariance of the weighted sum of x and y with a third random variable z. This is equal to alpha times the covariance of x with z plus beta times the covariance of y and z. And similarly, if we take the covariance of one random variable x with the weighted sum of two random variables y and z, this is equal to alpha times the covariance of x and y, so alpha is the weight applied to y, and beta times the covariance of x and z, where beta is the weight applied to z. Now we can briefly prove the statement. Let's prove the second one. The other one will follow analogously. So the covariance of x and alpha y plus beta z is equals to the expected value of the product of x and the other side, so that's the weighted average of y and z, minus the product of the expectations now this is equal to the expected value of x alpha y plus the expected value of x beta z, using the linearity of expectation here, minus the expected value of x times, and again using the linearity of expectation, we can write this as the sum of the expected values of y plus expected value of beta z. Now we can pull out all those constants here. So we have here the expected value of x, y, and now we use the corresponding term from here, minus again alpha in the front, expected value of x, expected value of y, plus beta times the expected value of x z, minus beta times the expected value of x times the expected value of z. And this here and this first term here is equal to alpha times the covariance of x y, and the second term is equal to beta times the covariance between x and z. We can take now the covariance, which does not lie in a particular value range, and normalize it to go from -1 to 1 only by dividing it by the square root of the product of the two variances. The resulting quantity is the so-called correlation between x and y. The correlation we typically define or denote by this Greek letter rho. So rho of x and y, the correlation between x and y, is given by the covariance between x and y divided by the square root of the variance of x times the square root of the variance of y. Correlation also measures the linear relationship between x and y. However, because we just normalized it, it lies in the value range of -1 to 1. And two variables are said to be uncorrelated if the covariance of x and y is equal to 0, which also implies that the correlation is equal to 0. So from 0 covariance, it follows that the correlation is also 0. Let's look at, again, an example. Here we have two samples from two-dimensional unimodal distributions. We said that correlation and covariance measure linear dependence between two variables. In this case, the two variables are the two components of these two-dimensional distributions, x and y. So we see that if we get large values of x, so for example this value here, we tend to get negative values of y. And if we get small values of x, values smaller than 0, we get large values of y. So the sign difference or tends to differ between x and y, which means that there's a negative correlation between them. You can also, if you draw a line through these points here, you see that this would have a negative slope, the line. And similarly, if you have a positive correlation, so for large values of x, we get large values of y. And for small values of x, we get small values of y. We speak of a positive correlation. And again, if you draw this line here, you would have, in this case, a positive slope. We said that correlation tells us something about the linear relationship between two variables. As a result, correlation alone is not sufficient to tell us all about all dependencies between x and y. And thus, two variables being uncorrelated, so their correlation being 0, is not enough to tell us that they're also independent of each other. In the other direction, it's true. So if the two variables are independent, then they're also uncorrelated. So if they're independent, there are no linear relationships between them. However, not having linear relationships doesn't mean that they're also independent, because they might have higher relationships. Let's look at a few examples. Here we see, for example, variables that are extremely strongly correlated, so correlation being 1, extremely strongly negatively correlated, and anything in between. For example, here we see correlation equals 0, which means that knowing something about x does not tell us something about linear relationships of y. However, this is not enough to tell us something about the dependence between x and y, because, and here we see many examples where there are no linear relationships, so the variables are in fact uncorrelated. However, there are dependencies between these two. For example, here, if you know where you are on this line, so if I give you the x value, And you know that this line exists and that all these points go around this y. Knowing the x coordinate tells you a lot about the y coordinate, right? So you would be able to basically do a nonlinear regression of x and y, and in this case as well. So, for example, if you know that x is here, you might either predict this value for y or this value for y. Now there's a third case where if, for example, there is no variance in one of the two dimensions. So here along the y-axis, the variance is equal to 0. Thus, the correlation is not defined because the correlation is the covariance divided by the product of the square roots of the variances. Now, if the variance of y is equal to 0, then we cannot divide by the square root of 0 because the square root of 0 is also 0. So the covariance would not be defined. Another example is the following. So we construct now two variables x and y that by definition are dependent on each other by defining y equals x squared. So we have a random variable x. The expected value of this random variable x is equal to 0. And we define a second random variable y equals x squared. So it's obviously dependent because it's deterministically defined based on x. We're just squaring that value. However, it is uncorrelated. The covariance between x and y, if we compute that, it's given by the expected value of x times y minus the product of the two expected values. Now the expected value of x is 0. So the product of the expected value of x and the expected value of y is 0. No matter what the expected value of y would be. And the expected value of x times y, well, if we plug in the formula for y, we get the expected value of x times x squared is equal to x cubed. We define x to have the expected value of x cubed equal to 0. Thus, the resulting covariance between x and y is also 0. In contrast to the expected value, variance is not linear because, in the definition it's squared. But we can show that if we weigh the random variable x with a constant and maybe add another constant to it, the variance of the resulting random variable will have the variance of the original variable x times alpha squared. So beta goes away. Well, we will see why that is the case. That's related to this adding of beta, just shifting the values and also the expected values by beta. And this scalar multiplication here will be a square of alpha. Let's briefly prove this. So the variance of alpha x plus beta is equals to the expected value of alpha x plus beta squared minus the expected value of alpha x plus beta squared. Now we can expand these terms. So here we have the expected value of, and let's expand this here, alpha squared x squared plus 2 alpha beta x plus beta squared minus, now the linearity of expectation tells us this is equal to the expected value of alpha times x plus beta, and the whole thing still squared. So now we can take these expectations. So again, we can use the linearity of expectation. So here we have the expected value of alpha squared x squared plus 2 alpha beta, the expected value of x plus beta squared. So there's no x in here. Minus, and now we can square all of these terms. So we get alpha squared expected value of x squared minus 2 times alpha beta expected value of x minus beta squared. We cancel a bunch of terms. So this goes away with this one. This term goes away with this here. And what we're left with is this term and this term. So this is equal to alpha squared times the expected value of x squared minus alpha squared times the expected value of x to the square, which is equals to alpha squared times the variance of x. So what we have just shown is that if there are multiplicative constants, two random variables, they are being pulled out and squared, and additive constants, such as this beta here, disappear because they just move the expectation, which then is again subtracted. If we have multiple random variables x1 through xn and they are uncorrelated, so all the covariances between the xi's and the xj's are 0, then the variance of their sum is equal to the sum of the variance. That is not the case if they are not uncorrelated, because then we get additional terms based on their covariance. However, if the covariance is equal to 0, then these terms go away. We're only left with the sum of the variances. As independence also implies uncorrelatedness, remember, not the other way around. However, independence also implies uncorrelatedness. It follows that also the variance of n independent random variables is equal to the variances, the sum of the variances.